Legend has it that in the 17th century, Sir Isaac Newton noticed an apple fall from a tree and began wondering why the fruit had fallen to the ground and not upward or sideways. Well, that would be freaky. After years of studying, he concluded that gravity must be the culprit. The scientist called it a force of attraction that existed between all objects. But it was Albert Einstein, many years later, that revolutionized these ideas about gravity. Legend also has it that he wasn't completely satisfied with Newton's findings. Something just didn't seem right. As a young scientist, Einstein had some trouble formulating his theories, trying to explain the behavior of moving objects. When an experiment came to his mind, he called it the happiest of thoughts. Gravity feels like the sensation of riding in an ascending elevator. He called it general relativity. Einstein began working tirelessly, trying to prove this idea. At one point, he even complained he was on the brink of losing his mind. Now, in the simplest terms, general relativity claims that gravity is the curvature or warping of space. The greater mass an object has, the more it warps the space around it. Imagine a heavy ball resting on a trampoline. The rubber sheet under it gets warped under its weight. It's the same with our sun. It's big enough to twist space across the entire solar system. That's why our planet, as well as all the others, orbit around the star. This warping also impacts how we measure time. If you look at your watch, time seems to go by at the same rate every day. But if you hike to the top of a mountain and your friend wanders through a valley at the bottom of this mountain, you'll see that your watches will calculate time differently. One watch will tick faster, while the hands of the second one, which is traveling through the valley, will move more slowly. That's because gravity affects how fast time goes by. With these experiments in mind, Einstein concluded that gravity was not a force of attraction, but rather a curvature in the fabric of space-time. We feel gravity as a force simply because we're placed on some surface. If there was no surface and no attraction between us and this surface, we would become weightless. If you don't mind getting some weird looks, try this experiment. You'll need a bathroom scale and an elevator to ride. You'll soon see that your weight fluctuates as you move up and down in the building in the elevator. The gravitational force is the same, but your weight is different because the elevator speeds up and slows down. Aboard the International Space Station, astronauts literally move along with the station, so there's nothing to push them against the side of the station so that they have some weight. Even if we still think of gravity as a force, it's the weakest one we know. First of all, it only attracts. There's no negative counterpart that could push things away. And weirdly, even though this force is strong enough to keep galaxies together, we still overcome it every day. Every time you lift an object off the floor, you overcome the force of gravity produced by the entire Earth. Ooh! Just to paint a better picture, Earth's gravitational pull is weaker than the power of a refrigerator magnet. The fact that our planet has gravity also affects the way we look and act. All creatures on Earth are limited in growth by the height of their skeleton and by how much weight it can carry, which is directly proportional to gravity. That's why some marine creatures can grow bigger. The largest animal on our planet right now is the Antarctic blue whale. It's about the size of 2 school buses combined. That's because sea creatures can float, which slightly counteracts gravity. The effects of gravity can be seen in people, too. We are taller in the morning than we are in the evening. Our everyday activities and the added effect of gravity make the cartilage in our ankles, knees, hips, back, and neck compress. Once you have overnight rest, the cartilage swells back to normal. Gravity might also affect your shower routine. That is, if you're an astronaut. They have to rely on the old-fashioned way of bathing up there on the space station. They can't take a shower since the force of gravity up there is different and water doesn't flow as it should. Instead, they use liquid soap, water, and no-rinse shampoo. They first squeeze some liquid soap and water from pre-made water pouches onto their skin. Next, they open the no-rinse shampoo and add a little water to wash their hair. Towels are then used to wipe off the excess water, which is really precious in space. To make sure they recycle it, an airflow system quickly evaporates excess water. Gravity and weight shouldn't be confused. Astronauts on the space station do float, and you may sometimes hear that they are in the state of zero gravity. It's far from the truth, though, since gravity up there is about 90% of its value on our planet. But astronauts look and feel weightless, since weight is the force a certain object exerts on them back on Earth. Most creatures have evolved to sense and adapt to Earth's gravitational pull. In the sea, for instance, some fish have floating calcium carbonate deposits in their heads. Scientists call them ear stones, and they're pulled down by gravity. They act like a fish's internal compass. Now, plants have evolved to grow starch grains in the tips of their roots. They use this amazing feature to force their roots deep down into the soil. As little as we seem to understand it these days, we do need gravity for way more things than we can imagine. For instance, some bacteria become even more dangerous in space where there's little to no gravity. Salmonella, for example, the type of bacteria that is known to cause food poisoning, becomes 3 times nastier in the condition of microgravity. So you really gotta cook your chicken. Our own moon stays where it is because of the effects of gravity, too. If it weren't for this force, our satellite would have floated away by now. But it's held in place by Earth's gravitational pull. Objects with the biggest gravitational pulls in the universe are black holes. Thankfully, our planet is really far away from any of them. Nothing can escape the gravitational pull of a black hole, not even light itself. Similarly, gravity is different on each planet, and because of that, things weigh differently depending on which planet they're on. Take Earth, for example. An object that weighs 100 pounds here would only be 38 pounds on Mercury. But if you're planning on losing weight fast, try booking a trip to Pluto. Someone who weighs 150 pounds on Earth would weigh no more than 10 pounds on Pluto. The same person would weigh considerably more on Jupiter, which is the planet with the most powerful gravity. 150 pounds on Earth would turn into more than 354 pounds there. No thanks. Remember that experiment with watches ticking at different levels of elevation? It turns out that gravity isn't spread evenly on the surface of Earth. Why? Because our planet isn't a perfect sphere. The mass of Earth isn't evenly distributed either. That's why you get variations in gravity in different locations. More so, gravity is weaker at the equator because of the centrifugal forces produced by the planet's rotation. Since we've always perceived gravity as a force, we seem to believe that it has somewhat of a suction motion. But it's not exactly true. Back in 1998, scientists were baffled to see that the expansion of the universe was speeding up. So they linked this to the repulsive gravity of mysterious dark energy. We now know that dark energy makes up for more than 60% of the mass energy of our whole universe. But since nobody knows what it actually is, we can only make assumptions. And one that's largely accepted is quantum theory, which seems to claim that gravity pushes rather than pulls things in. You got all that? I may need to watch this one again.
You might not think about gravity much, but it affects everything we do. It's the reason why things fall down instead of flying up. It keeps us connected to the Earth, so we don't float away into space when we jump. But for physicists, gravity is something more. It's a fascinating puzzle that needs to be solved to understand how the universe works, and they're on a quest to uncover its secrets. So what's so mysterious about it? Let's see. We've learned a lot about gravity from the legendary Isaac Newton. He was the first to invent the law of gravitation. He taught us that any two objects in the universe can't help but be attracted to each other. It's like they have this secret gravitational crush going on. How strong this attraction is depends on two things: how big the objects are, that is their mass, and how close they are to each other. But here's where it gets cool. Gravity isn't just a two-object dance. It's a complex space choreography. Take our solar system, for example. The sun plays the lead role, using its gravitational pull to keep all the planets in their orbits. But each planet also has its own gravitational mojo, tugging at the sun and even its neighboring planets. Then, a few hundred years later, another hero, Albert Einstein, took gravity to a whole new level. He described the theory of general relativity. According to Einstein, gravity isn't just a regular force. In reality, it's curving and warping the fabric of spacetime. Think of it as a heavyweight champion sitting on a rubber sheet. The sheet bends and curves under the weight, and the smaller objects nearby can't help but roll towards the heavyweight. Now, even though we can't see space's curves with our own eyes, we can see what happens to objects that get caught in its grasp. Getting pulled by gravity is like being caught in a whirlwind of forces. The caught object starts spiraling downward, just like a coin in those penny slot cyclone machines you find at tourist shops. Or it might move gracefully in circles, like bicycles racing around a velodrome track. Gravity is the primordial force that guides our entire world. Without it, there would be no stars, no galaxies, nothing. But where does it come from? Well, that's the million-dollar question. And we don't have a complete answer just yet. But we do have some guesses. First of all, we know that gravity is more than just a feature of space. It's a force that pulls things together. Surprisingly, it's the weakest force among them all. But let's take a different look at gravity. Something that may surprise you. Instead of being a force that directly pushes or pulls objects from a distance, it's more like a dance. Gravity, as amazing as it is, doesn't perform alone in this dance. It shares the spotlight with other forces, like electromagnetism, for example. Let's imagine two electrons. There are dancers. Now, they don't directly push or pull each other like you might expect. Instead, one electron creates a special kind of field around itself, like an invisible force field. This field sets the stage for the show. The other electron senses this field and starts to twirl and interact with it. It's like they're following some choreography. And when we watch this dance, it looks as if the second electron is being pushed or pulled by the first one. But in reality, it's all about the intricate movements and interplay between the dancers and the field they're dancing in. The dancers never touch each other directly, but their interactions through these fields make it seem like they're connected. It's a magical display of fields and movements coming together to create the illusion of forces at play. The thing we call gravity. So even though it's not a force in the usual way, it behaves like one. We call it an emergent force, because it emerges or comes out from the way space and objects interact. Which is why, if we want to get technical, some scientists prefer to avoid the words gravitational force and opt for the term interaction. It's just a way for particles to mingle and exchange energy and information. Electromagnetic interactions, gravitational interactions, they're all part of this grand soiree. At least that's one of the theories. Some scientists also think that gravity might be made up of tiny particles called gravitons. These sneaky particles work behind the scenes, making objects attract each other. However, we haven't been able to directly see these elusive gravitons yet. So, according to this theory, gravity is both a force and a potential particle. As you can see, we have some struggles with explaining how gravity works on a large scale. But at least we have a good understanding of how it behaves in certain situations, like how planets orbit the sun, or how objects fall to the ground and stuff. But what happens when we zoom into the atomic scale? And what if we venture into the depths of black holes and the Big Bang? Now here's where gravity's wild ride goes off the rails. First, let's enter the realm of quantum mechanics. There's something peculiar that happens in this tiny world. Gravity, the force that pulls things together, seems to take a back seat. On a microscopic scale, other forces like electromagnetism take the spotlight and become the superstars. They're overshadowing gravity, and this leaves scientists scratching their heads, wondering, is this possible? Why does gravity suddenly fade away? So far, we have no idea. And when it comes to the grandest scales, where immense objects like black holes, gravity takes on a whole new level of complexity. For example, inside a black hole, laws of physics and gravity, as we know them, basically fall apart. It also decays when we try to understand how gravity behaved immediately after the Big Bang. Where did it even come from? We have no idea. In other words, we find ourselves in a cosmic fog when it comes to understanding gravity. But fear not, scientists are working hard to learn more about this enigmatic emergent force. They're doing all sorts of experiments and using fancy technology to crack its code. Even though we still have a lot to figure out, we're making progress every day. For example, have you ever heard of gravitational lensing? It's like a mesmerizing magic trick. Imagine a beam of light as a fearless explorer, taking a straight path through the universe. But as it encounters the gravitational pull of a massive object, the light's journey becomes a wild roller coaster ride. The gravity of the massive object bends the fabric of spacetime, creating a funhouse mirror effect. Our brave beam of light finds itself curving and twisting around the massive object, following a new unexpected path. But as the light changes its trajectory, it also reveals to us distant and hidden wonders that would have remained invisible otherwise. The light can magnify, distort, or even create multiple images of faraway objects. So all the things that have been playing hide and seek with us finally become visible, like black holes. There's also a mind-blowing idea called gravitational waves. Einstein predicted their existence tens of years ago, but only recently have we finally been able to confirm them. And that was a huge breakthrough in the science world. These waves carry the echoes of cataclysmic cosmic events, such as the collision of massive black holes or the birth of newborn stars. Just like dropping a pebble into a serene pond, these crazy events cause a ripple effect. But instead of water, it's space-time itself that ripples and warps. Scientists have just recently developed a way to listen to these whispers. They've created instruments capable of detecting these gravitational waves. These instruments, known as interferometers, are like ears that are finely tuned to catch the subtle vibrations of the universe. But one thing's for sure. Gravity is a superstar that shapes our universe. It keeps everything around us connected and rules our entire universe. The quest to unveil its ultimate secrets continues, and it's a thrilling adventure for scientists and curious minds alike.
How would you describe the shape of the planet we live on? It's definitely round, but it's not a perfect sphere. Because of the force of Earth's rotation, it's slightly flat on the north and south pole. But there's more to it. The planet's rotation causes its sides to bulge outwards. The best term to describe our home planet is ellipsoid. Earth is nothing more than an oversized lumpy potato. These are the words of Atraji Ghosh, a solid Earth geophysicist from Bangalore. She and her team have been studying something called the Indian Ocean Gravity Hole. Sounds like the scenario for a science fiction movie, but it's very much real. We think of gravity as something consistent. If you drop a pen from your hand in Los Angeles and in Perth, they're going to fall to the floor at the same time. Well, this is not completely true. Gravity is connected with the mass of a celestial body. Astronauts on the surface of our moon don't walk, but move in hops. That's because Earth weighs 81 times more than the moon. Less mass means less gravity. Earth is more massive, so it has a stronger gravitational pull. But there's a catch. All this mass isn't distributed evenly across the planet. As a result, gravity varies as well. NASA has been mapping Earth's gravity field since 2002 using twin GRACE satellites. The maps they produced show where gravity is stronger and where it's weaker. Mountain ranges such as the Himalayas contain a lot of mass. This means they generate a stronger gravity field. The opposite happens in ocean trenches. The deepest of them is the Mariana Trench in the Pacific Ocean. You could almost stack 2 Mount Kilimanjaros inside it. The low concentration of Earth's mass below it means that the gravity field here is weaker. Places on the globe where huge chunks of mass are missing are called geoid lows. A geoid is an imaginary surface that follows the outline of sea levels around our planet. Imagine the Earth without any land. That shouldn't be too hard since the nickname of our home is Blue Planet. Now draw a curvy line along the surface of the oceans, and you get a geoid. In reality, the line stretches across oceans, as well as land masses. Scientists use this imaginary line to calculate the depth of tremors or objects that occur underground. When the wavy line goes down, that's a geoid low. The biggest of them sits at the bottom of the Indian Ocean. The first to discover it was a Dutch geophysicist in 1948. He was performing a gravity survey from a ship. The man noticed that sea levels dipped over 320 feet below the global average. The gravity hole got the official name Indian Ocean Geoid Low. It spans well over 1 million square miles off the southern coast of India. If you went out at sea in the middle of the gravity hole, you wouldn't notice much, just an endless ocean as far as the eye could see. The only way to measure the dip in gravity is through extensive geophysical measurements and calculations. The concept of a gravitational hole existed for nearly 2 centuries in the scientific community, but researchers could study it in high detail only after satellite measurements became possible in the late 20th century. A team of Indian scientists was determined to explain the anomaly that had been puzzling geologists for decades. They used supercomputers to simulate the seismic activity that formed our planet. A total of 19 simulations revealed how tectonic plates moved across the span of over 140 million years. This was during the Cretaceous period, the time when T-Rex roamed the Earth. Nearly a third of the possible scenarios produced a geoid low, similar to the one in the Indian Ocean. The most important factor in these models was the presence of magma plumes. These are places inside the Earth's mantle, where lava flows upwards. The mantle sits between the planet's outer core and the thin crust we walk upon. The magma in the mantle plume is hotter than the surrounding rocks. The heat it generates melts and thins the crust. This creates hotspots that are brimming with volcanic activity. Yellowstone National Park and the Hawaiian Islands sit atop such hotspots. The Indian team of scientists linked the presence of magma plumes to the formation of the geoid low. Their source was an ancient ocean that disappeared tens of millions of years ago. It was located where the Himalayan mountain range sits today. Evidence of this lie in the marine rocks researchers found on the world's tallest mountains. The oceans ceased to exist when India's landmass separated from the supercontinent called Gondwana. It drifted north and merged with the rest of the Asian continent. At the time, the Eurasian supercontinent was called Laurasia. The Indian tectonic plate went down inside the mantle. It ended up under the African continent. This landmass contained a lot of crystallized material which was quite dense. When the sinking plate of the former ocean reached it, plumes of magma spilled out. As a result, low-density materials ended up closer to Earth's surface. Density is used to calculate mass, and if you remember our lesson in physics from the beginning of the video, less mass translates into a weaker gravity field. Scientists believe this is how the geoid low in the Indian Ocean formed some 20 million years ago. At this point in prehistory, the Earth looked a lot like it does today. There were vast grasslands, and whales swam in the seas. Geophysicists who created the computer model cannot tell for sure what will happen in the future. Ghosh thinks it's possible that the gravity hole in the Indian Ocean will remain in place for a long time. But plate movements can also cause the anomaly to fully disappear in the coming eons. Earth's tectonic plates are constantly shifting. They define the shape of our continents and oceans. Experts study plate movements to get a picture of how our world looked millions of years ago. However, telling Earth's geologic future is much more complex. The gravity hole in the Indian Ocean is the biggest, but it's not the only one in the world. Other areas with low gravity include the island of Cuba and the Bahamas. On the opposite side of the spectrum are the Philippines. Here, gravity is stronger than normal, but the poles are the places with the strongest pull to them. They are the closest to the center of the Earth. If you stand directly on the North or the South Pole, you are 3,950 miles from the planet's core. At sea level on the equator, this distance increases by more than 13 miles. Earth's gravitational field also has an effect on your weight. At the equator, you weigh 1% less than you do on the poles. The South Pole is maybe more suitable for this experiment because there is actually ground there. But gravity is the strongest at the North Pole in the middle of the Arctic Ocean. This is where scientists in 2013 recorded the highest gravitational acceleration on the planet. This is the rate a falling object speeds up in free fall. The acceleration depends on the strength of gravity. When a team of researchers from a university in Perth set out to map these gravity changes, they discovered something interesting. Gravitational acceleration was the highest at the surface of the Arctic Ocean. This is something they expect to find, but the location of the lowest acceleration point amazed them. It wasn't on the equator as they assumed. The spot lay more than 600 miles south of it at Mount Huascarán in Peru. Scientists believe that the mountain's height had an effect on the phenomenon. This peak in the Andes is the highest point in the South American country. Hypothetically speaking, if a human falls from a height of 330 feet here they will reach the ground 16 milliseconds later than if they performed the same stunt in the Arctic.